So in this video, we're going to look at the properties, the general properties really of cubic functions. In blue here, I have f at x is equal to x cubed, and this is really just the parent graph or the general graph where we have the line crossing at the origin, or y is equal to 0. Now, much like the linear functions, the domain and range are all real numbers when it comes to the properties of cubic functions. Now, unlike the quadratic functions, they don't just have one min or max when it comes to the range. In fact, they have what we call a local maximum and a local minimum. Now, to communicate the rest of the properties of a cubic function, I've decided to graph another cubic function that has some stretches and compressions and translations. So this is a graph of x cubed minus 4x squared plus 3x plus 1. And so what we could see from this, as I kind of alluded to before, is you have what is called a local minimum and then a local maximum. The local minimum is located where the graph opens upwards, and the local maximum is located where the graph opens downwards. One of the trends of cubic functions is that they have local minimum and a local maximum. Now, another word for these are called turning points. In terms of the intercepts, they have one y-intercept, and then in another color here, they have 1, 2, and 3 x-intercepts. And that's if there's all real roots present. Okay, so the min and maximum regions are where the graph actually turns. They're not points, right? It's not like a min or a max point like in a quadratic, but it's areas. So it'd be like this entire area here where the graph, or regions, where the graph actually turns. So if we look at the local maximum, the graph turns downwards. And we look at the local minimum, the graph then turns upwards after going down from the local maximum. Now, when we talk about end behaviors, remember we're talking about what happens to the y as x increases. And so as the x increases, so as we read the graph from left to right going this way, we can see that generally the y increases, and this would be if the leading coefficient, and remember that's the coefficient in front of the highest degree, so if the leading coefficient is positive. Now in this case, the leading coefficient for the x cubed over here is a positive 1. So in this case, we can see that as we go more towards this way, your y values keep going up and up and up almost infinitely. Now the point in purple over here is called an inflection point. And these are points where the curve changes, okay? So it goes drastically from, let's say, going upwards or concaving up to concaving down. Now, what happens if we simply inverse the sign or reverse the sign of the leading coefficient? So instead of x cubed, it's now negative x cubed. Well, a lot of it stays the same. We still have our domain with x all real numbers, and the range is still going to have, which is the y values. We can write it as r. I wrote it as y, but we can write it as r here, which is going to be y is equal to all real numbers, or infinity. And there's still going to be a local maximum, which is over here, so local maximum. There's also a local minimum all the way down here. It's just way down, but this is a local minimum. The only difference is, I'm going to put a star here and clarify this, that the local maxes and mins reverse positions. You still have the 3 x-intercepts, which are outlined in green over here, you still have the 1y-intercept, which is now outlined in blue. And with regards to the n behaviors, what we notice is that as x decreases or moves more towards the left here, then y actually increases, right? Y continuously goes up. But if x increases or moves towards the right, then we can see that the y decreases. So the n behaviors and the local max and the min, when you reverse the sign of the leading coefficient, they reverse as well. So if you reverse the sign, then the local max and min and the n behaviors also reverse when it comes to cubic functions.